Thank you. Thanks everyone for coming. We're going to talk to you today about Xous. It's a pure Rust rethink of the embedded OS, and also talk a little bit about Baochip, which is some custom silicon for running Xous. Without any further delay, we'll get started. Once upon a time, Zobs and I were sitting around having a beer, as many good stories start. This was a few years ago before COVID. We wanted to build a secure embedded OS. And we came to the conclusion that we shouldn't let POSIX get in the way of any good ideas. But we also wanted to have memory safety, and so we would use pure Rust, which was like kind of a new thing at the time. And we also thought it'd be great to have some sort of hardware memory protection, but how will we do this? Like techniques like Cherry were not really mature at the time. A bunch of the hardware memory protection stuff was a bit proprietary. And so we thought maybe we'd use a memory management unit, right? Memory management units were invented in 1960. They're super old, like these sort of museum-grade computers had them on the inside. And it gives you stuff like page-level memory protection, hypervisors, virtual address spaces, swap memory. Seems like a pretty cool idea, right? And MMUs have been integrated in CPUs for a long time. So in like the 386 CPU, you had it since 1985. And I've highlighted like the amount of space that the MMU takes on the die there. You can see it's not overly huge. And it's also many instruction set architectures. The 6830 started integrating it in 1987. And the MMUs, you can see how big it is on that die. So, can we just MMU all the things? Like, MMUs are in a lot of chips, and a lot of OSes use MMUs, and the market sort of expects to have memory security in OSes, and therefore the chips integrate this sort of thing. Well, not so fast. During the rise of IoT and embedded, cheap, insecure computers came up everywhere. So there was sort of a split in the road between what eventually became the Cortex-A and the Cortex-M line. The Cortex-A line, sort of turned into like the bigger CPUs we know today, and the Cortex-M turned into stuff like the ARM 7 TDMI. This thing, the ARM 7 TDMI, was wildly successful. I think everyone here in the audience probably has owned several of these in their lifetime. 10 billion units shipped. There were Nokia phones and Nintendo Game Boys, iPods, and so on and so forth. Super low royalty. And it's kind of what took ARM from being like a kind of obscure player to a dominant player in the CPU architecture market. They were focused on the low-cost embedded applications. So typically those applications only integrate a few kilobytes of RAM, dozens of kilobytes of ROM. So there's no room for an MMU in that type of application. This is what eventually evolved into what we know as the Cortex-M product line today. But this also sort of created a new sort of power cycle of poor memory security and embedded IoT, right? We had CPUs without MMUs, which meant we wrote OSes that didn't assume MMUs or memory security, and then the market was just okay with it, right? Because they got something cheap and whatever, so it was hackable or could crash or whatever it is. And so then no one made CPUs that required it, and so on and so forth. And so the question is there a way for us to break that power cycle, right? The problem is you can't install an OS that doesn't exist, right? Well, if you want to write an OS, you can't write an OS for a CPU that doesn't exist, and you don't make CPUs when people aren't asking for those CPUs, right? And so then the problem is, are we just going to be insecure forever? Is this just the status quo of situations? Well, I thought maybe if we ask nicely, we can have nice things. If you remember those die shots I showed you earlier of how big the MMU is relative to the CPU, if you look at this sort of SoC here, this is a ATSAM SoC. That little corner in the lower hand corner is the CPU core. If you could imagine taking an MMU and wedging it in there, it's a very, very small portion of the overall silicon. It's not a huge amount of area, so it seems like a reasonable thing to ask for, right? It's old tech, there's no patents, just a couple % extra area, and we could have all these great time-tested benefits for memory security, right? Wrong. The problem is ARM will not allow that to happen. And the reason is that ARM charges what I call the Linux tax. So the Linux kernel, like for example in Android, requires an MMU to run. Cortex-A has the MMU, Cortex-M does not. ARM charges a lot more for the Cortex-A in terms of upfront costs and royalties than the Cortex-M. This is the Linux tax. In order to protect their profits, they don't want any Cortex-Ms to have an MMU, because then you could start using these lower-end Cortex-M cores in some of the cheaper applications. They want you to pay that Linux tax. Therefore, everything in this sort of M class is going to never have an MMU. Right? And if you want memory safety, sure. They came up with a proprietary solution, the MPU. And a bunch of Libre OSes have targeted this, but this just further entrenches their power and gets more vendor lock-in into the market. So ARM's message to embedded developers that want memory security is that you can't have it unless you pay them. Also, thanks for helping us build the moat and defending it, and we're still going to charge you to cross the moat. But I'm old and I'm stubborn. And I remember an internet before the DMCA, and I recommend you try it, everybody. And I also remember hardware before ARM, right? So I was actually born closer to those machines over there in the museum than this machine over here, right? So back in my day, we had MMUs. And then in the open source community is strong, right? RISC-V is an open architecture specification. You can just get a CPU core that has an MMU on the inside. It's FPGA friendly. It's tape-out proven. It's the sort of thing that now exists inside of the community. So we built an FPGA-based SoC with an MMU unit. That's the little thing that we circled up there on top of the whole bunch of peripherals underneath it. And we managed to say, OK, step one, we now have an SoC with an MMU. Awesome, right? Now we just need to go ahead and run an OS that requires an MMU. Oh, wait, those don't really exist. So I then went to Zobs with a blank sheet with 2 words scribbled on it, Rust and MMU, and he went and invented Xous. And so this is, Zobs will tell you like how to do the rest of the L.
Thanks, Bunny. So the requirement is we have an MMU. Now, what is an MMU? He kind of went over some of them. But the thing is, there are a lot of different kinds of MMUs available. So we kind of have to define the problem. We need an MMU that can manage the entire address space. There are chips available that have an MMU that can manage, for example, the SPI flash or certain areas of memory. But we want something that can manage all of RAM. We also don't want to be working on individual bytes or words. We want to have page size granularity. And because most of the memory in a microcontroller doesn't exist, it's mostly blank space, we want to have multiple levels of page tables so that we don't have to pay the penalty of having a page table for an area of memory that doesn't exist. We also want process isolation. So we don't want to have any arbitrary process be able to change its memory mapping and give itself access to things we don't. We want to be able to isolate it, and if it tries to change something that we don't want, we want to actually cause a violation in that program. And we also want fast switching. So we don't want to have a system with an MMU where we have to rewrite the page tables in order to switch from one process to the next. We want to make it as quick as possible to do that. So if you're more of a graphical kind of person, if you want to divide physical memory up to something that looks like this, with these squares representing 4K bytes, we want to be able to manage which 4K bytes are available to which process. And so what this ends up looking like is on the left side there, you have the virtual process memory. And any arbitrary square in there, thanks to the MMU, can map to any arbitrary square in physical memory. And at least on RISC-V, this is done with this register called the SATP, the Supervisory Address Translation and Protection Register, that is basically an entire 4K page full of these descriptors. So in the end, you can actually have multiple processes that are all running in the system, along with the kernel on the side. But interestingly enough, these are all actually linked at exactly the same address. I don't know if you've ever actually run a compiler and had to provide a linker script, but interestingly enough, these all are linked at the exact same address because they're all completely isolated. You can kind of think of it as a hypervisor of unikernels if you want, but really, they have no way of communicating with each other. They don't have access to the memory of any other process. Even the kernel, in this case, cannot access memory of the processes without rewriting their page tables. So in this system, every bubble is completely isolated, including the kernel. So we kind of have these islands that really have no way of talking. So we need to get a way for these processes that are isolated in this sea of individual memory accesses. We need to figure out how to get them to communicate. And a common way of doing this is message passing. And at a high level, message passing is where you have source A of some sort that sends a message of some sort to destination B, which tells you exactly nothing about how we want to actually do message passing. So we need to define some requirements. These messages that we pass, what is in them? What is the contents of the message? how do you receive messages? Are they one way, or they send receive kind of a reply response type thing? Let's just come up with some goals to decide how we're actually going to set this up. The first goal here is we want to be able to send scalars. And by that, I mean we have a sender of some sort, and we want to be able to send an integer through that pipe and have it pop out in the other process on the other side. Okay, so that's one thing we're going to try doing. What about memory? Wouldn't it be neat to be able to send memory from one process to the next? Say maybe we have an array of 10 values that are integers, that are U8s. What if we actually sent that array across this mythical message passing system and got it out on the other side, and maybe we can actually modify the array and send it back? That sounds kind of nice. Actually, we kind of can do that because we have an MMU in this system. As long as the array we're sending is the size of a page and is page aligned, we can actually just detach that page from one process and reattach it to the next and update it in the other process. And then when we're done, send it back. But, that sounds kind of dangerous. Like doing things like detaching your stack and attaching it to another process, that sounds kind of dangerous. Like what if things go wrong? Well, a lot of you here have done Rust, and this is kind of what Rust is all about, this safety. Because remember, the number one thing in Rust is that each piece of data can only be owned by one person, or one entity. And from this, you kind of get the concept in Rust of a piece of data is either mutable or it's shared and available as a read-only copy to multiple processes. And from these rules, you actually get this motif that gets repeated in Rust, where you have things that are either move, borrow, or mutable borrow. So in the first function there, A is a string that is moved when you make this function call, which means it's no longer available in the source function. B there is borrowed, which means that we now know that no other part of this program during the course of this function will be able to update that value. It's fixed. And in contrast, the third value there is mutable, and we know that nobody else will have a copy of that. And you actually see this motif repeatedly. You see this on trait implementations, on enums and structs, where you still have the same move, borrow, and mutable borrow of that trait object itself. You also see it in other places, like in function closures. They have the same move, borrow, and mut borrow. If you more about graphical, what we can actually do is when we send this message, that 4K message from one process to the next, we can actually just detach that page from the source process and just reattach it to the destination process. So that memory becomes unavailable in process A until process B returns it. And this is actually the memory management unit is now going to enforce the rules of Rust for us automatically. So if there's a violation, rather than using a Rust construct such as a ref cell or something like that, the hardware is actually going to enforce this for it. If you remember this descriptor from a couple of slides ago, there are actually bits down here for execute, write, read, and valid. So in order to move it, all we have to do, it's a very simple process of just disabling the valid bit, and when we move it over, if it's a read-only borrow, then we just have to make sure that the W bit is cleared. And if that's violated, the hardware will enforce this for us. So the Rust semantics are actually enforced by this MMU automatically. And it's kind of a nice side effect. If you look at microcontrollers, the peripherals in there are actually just memory addresses. So this whole there's a single owner of a memory address. This means that drivers are managed by one process at a time, and it just kind of naturally falls out of this whole system. So with that in mind, let's talk about the basic messaging architecture that we're going to implement here. Now, we actually drew some inspiration from Helen OS and QNX, and I've been told that this design is actually very similar to how Solaris doors work. So we're going to need a server of some sort. And we decided that the best way to do this is to have server addresses be 128 bits. And so you're going to want to connect to the server address in order to actually send a message. And this server name is either a well-known 128-bit value, or if you want, it's actually possible to make it a random 128-bit value to connect to the server.
Yeah, and I really like that random 120-bit value because from a security perspective, it means we can now make completely hidden services that you can't discover because you'd have to guess that 120-bit number for communication between processes. So I think that's a pretty neat feature.
Yep. So with that in mind, the server name is 128 bits, which works out to 16 characters. As an example of how you'd create a server, you would call this function create server and then pass the 16-bit value in there as the argument, and you'd get your server out. If that server happens to already be created, you would get an error, but ultimately you create the server this way, and then you just pass that to receive message. So conceptually, this is what it looks like. It's actually very close to the way the real implementation goes. The actual implementation of the message is slightly different, but ultimately you create the server, and then you constantly receive messages on that, and you act on those messages as the server. As the client, it's very similar. It's the opposite, where you connect to the server by passing the address there. If the server doesn't exist, this will actually block until the server is created. And this means that when you're starting up a new system, you don't have to worry so much about concurrency because it will wait until the server is available. So for example, the printf function, the printf function is provided by a server. This connect won't succeed until the server is actually started. And then once you have that connection, you just call scalar message or lend or whatever on that, and that's how you actually send a message to this other server. Lend messages means you can pass references to memory, to slices, as long as they are page aligned and pages in length. And from this, you actually get the different message types that we support. There's the move, borrow, and mutable borrow again. For move, you can either send memory, which detaches it from your process and actually moves it wholesale into the other process. And that means you never can see that memory again because it has now been moved into the process memory space of the server. For just numbers, you can send scalars. And the interesting bit about this is that these two in red are actually non-blocking because you've moved the memory to another process. Why would you have to wait for it to respond? There's not going to be a response. So as soon as you send memory or send a scalar value, your program just continues executing. In contrast, for borrow, if you're borrowing memory to the other process, if you're lending it, then that is a lend message. And if the memory that you're lending is mutable, it's a lend mut. And for scalar, there really is no difference between a borrow and a mutable borrow. So both of these use blocking scalars, which return 5 scalar values back. So that is the basic messaging architecture, but of course messaging architecture does not an operating system make. So let's go over the actual implementation a bit. And I'm going to start with the tick timer, because anytime you start a new operating system, one of the first things that you work on is the timing system. How do you get the quantum going? How do you switch between processes? So the tick timer takes ownership of the hardware timer on the particular bit of hardware. This might be the SysTick on an ARM platform if we had one, but this is a special hardware timer that existed on the precursor Betrusted board. It starts it when the system boots, and this is how you get the uptime count. So this is a continuously incrementing counter. You can actually set an interrupt to fire when it hits a certain value, and that will cause the tick timer to send this return to parent sys call to the kernel, which is actually really interesting because this is a user space process, and it has this timer that is running, and it causes this interrupt, and this is actually the source of preemption in Xous. There's no kernel level scheduler inside the kernel itself. It's just a user space process that is periodically telling the kernel, hey, stop running this process and run the next one. So we actually have preemption because of a user space process. It also provides msleep. So in your process, when you want to sleep for a given amount of time, you just send a message to msleep. And here's actually what that looks like. So this is a implementation that you might have of sleep. And in Rust, duration is an amount of time. And in order to do an msleep, all you do is you make a connection to the tick timer server. Fun fact, tick timer-server is exactly 16 characters. So that's exactly 128 bits, which I thought was kind of nice. And then you send a blocking scalar to the tick timer server. Opcode 1 happens to be sleep ms, and you just provide it the duration as milliseconds. And what will happen is that message will get sent to the tick timer server, and it'll just kind of hold on to that message until the amount of time is passed. And because blocking scalar is a blocking call, it will actually block until the tick timer server returns that message. And so this is just kind of an example of how using these message passing primitives, you can actually build up entire operating system level primitives from just these common message passing primitives. Here's how you do the log server, for example. I mentioned this construct earlier where you create a buffer on the stack that is page aligned and page sized. All we have to do is allocate one of those on the stack and then use writeLine to write a value into that. And then now we have a buffer that we can very easily pass to the log server. Sadly, log server is only 15 characters and not 16, but you can't have everything. So you pass opcode number 1 for the standard output, the contents of the buffer, and because the buffer is a 4K page, you don't want to be printing out the whole thing because it's mostly going to be nulls. So we actually use 2 of the leftover scalar values to indicate how long the message is. And using this, that's how you do printline. That's how you do printline. So we actually took all of these. Those 2 examples, the sleep and the logging example, are actually from the standard library. We actually have Rust standard library support. Every 6 weeks, we build the current latest stable of Rust and come up with a zip file that if you extract that to your Rust sysroot directory that's managed by RustUp, you actually get a full Rust toolchain that is able to natively build binaries for this operating system. So out of all of this, as I mentioned, we're a tier 3 Rust target. Amazingly enough, we've done this all using stable Rust, so we've avoided using nightly Rust, and anytime we had something that needed stabilized, we've worked to get that upstream. One of the nice things about this is you don't need a C compiler for any of this. You don't need a C linker, you don't need a C compiler, unless you're running crates that require a C compiler. You don't have to worry about any of that when you're installing this. But most importantly, we're just using Rust semantics, and we're getting hardware MMU enforcing those semantics. So if something goes wrong, the hardware will flag an error, and the program will crash. So with all that, there you go.
And thanks. And with that, Xous exists. It's stable Rust, so we're not using any nightly, which that was a great decision by Zobs. It's simple, even kind of a humble hardware guy like me can maintain the kernel. Safe, and we have a standard library. And I want to say that this is one of the few code bases I've had that has gotten more fun to maintain over time versus less fun to maintain over time. So I really appreciate all the effort you put into it, and thank you very much for putting that together. And so then, here we are. Step 2, run an OS that requires an MMU. Well, now we can run Xous. Great. So are we all MMU yet? The answer is no. Unfortunately, our FPGA-based system is quite expensive. You can buy it. It's like $590. It's a 5x premium over silicon or something, also 5x the power. And it turns out that this is just too high a price to pay for security. In practice, everyone says they want security, but no one wants to pay for it, right? That's just the reality of it. So if we want people to actually use this thing, we're going to have to come up with a custom chip in order to get to the price parity which people expect in these types of devices. But there's several problems with custom silicon. Problem number 1, it's a literal black box. If I hand you a chip that's in a black plastic package, you don't know what's on the inside. So that you've lost some amount of trust and transparency there. Problem number 2, it's a figurative black box. There are no open RTL security-oriented ICs. There's no open PDKs and more advanced nodes yet. And so there's that openness issue as well. And then problem number 3, it's very expensive. You want to do a tape out and in sort of a more modern node, it's on the order of millions of dollars. Well, problem number 1, good news. Last year I gave a talk at 3C3 about addressing that. There's a technique that I dub IRIS, infrared in situ. It's a method for inspecting chips packaged with exposed silicon after they've been assembled to a PCB without damage. And so this little GIF loop here shows a chip that is mounted on a motherboard, and it starts to get pinkish there. That's the infrared light turning on, and you can actually see these ghostly figures. Those are actually the transistors of the chip that are reflecting light back, and you can sort of actually see what's going on inside the chip. So this kind of helps get past that first literal black box problem of having an IC versus being able to see the RTL and compile it to an FPGA. Problem number 2, openness. So there's been strong progress in sort of the open source silicon space. Today, 130 nanometer fully open PDKs exist. You can go to tinytapeout.com or wafer.space to go ahead and build chips and order whole wafers of them. The problem is that at that level of integration, there's only a few kilobytes of RAM on a chip. It runs at dozens of megahertz, and there's no like ROM technology yet in those PDKs. It's not really quite enough for Xous. And the problem is that we're several years away, in my reckoning, before we have a fully built out sort of PDK that can run in a more modern node. And so one option is maybe we just sort of wait for that to happen, but I would argue we actually can't afford to wait for perfectly open silicon, because the problem is every line of code towards ARM is a line of code towards their monopoly. So if we decided instead of like doing this, we would just port our stuff to a Cortex-A or towards their like custom MPU units, we would actually be supporting that particular situation. And so by waiting for open silicon, perfectly open silicon, it will make it harder to break free and adopt open silicon when it becomes available. So the question I have is what we do now to shift the momentum, right? It turns out we can just do some things now, right? So we can do partially open RTL. So the things, RTL is register transfer language, so it's harder described in code, Verilog and VHDL. There's an example of what the code looks like to describe some bits of hardware. And the thing is the things that we write, we can like open source, we can assign the license to it. We can choose open architectures for our CPUs today, and we can start building software today that will eventually run on this full open source hardware stack in the future, right? So there are things we can do, great. But problem number 3, it's expensive, right? So the cost of tools to build your own code is approximately $0.00, including like the power and the bandwidth it took to download it. If you want to build a chip, in the sort of maybe the most generous sense, it would be a few $1,000,000 for the mass set. It could be billions of dollars if you insist on having a full open fab, right? So how do we get past this? So bear with me. I have an idea. Maybe we could hitchhike open source cores on a commercial tape-out, right? So someone else can pay for it, but we're actually just hitchhiking along for the ride. And to get an idea of how this works is that if we look at the logic density in a small node chip, on the right-hand side here is an exemplar chip in 22 nanometer. If you look at this die shot, the bottom part of it is ROM, which is actually a third of it. A very, very large part of it is RAM. There's some analog stuff on the top left, and you have this logic in it. It's only about 20% of the area. And if you go ahead and you zoom in on the logic and see how dense that logic is, it's actually quite sparse. In that very, very top part there, you see a bunch of little small colored boxes. Those are the logic, and the gray stuff behind it is unused dead silicon. Right? So logic is a bit like a gas. It fills all the extra space available, and it's actually pretty sparse, even in these particularly high-end nodes. So if you think about a typical SoC block diagram, if you go to open up your data sheet for an STM, whatever it is, there'll be some Cortex-M sitting on top, talking through a bus fabric, and then on the bottom side of it, you have these peripherals, RAM and ROM, all this sort of stuff. And that bus fabric is capable of handling multiple cores, and you have multiple CPU cores on the top. Question is, can we just throw a RISC-V core right on top of that instead of having it being all ARM? Well, turns out, yes, you can. There's already a chip out there you can buy that does this, the RP2350. And then actually, if you go ahead and you do the analysis of it, what does it take to sort of do this? It turns out that these cores are incredibly, incredibly tiny. So this chip here, if you were to throw 4 pico RV32s and a Vexris CPU on top of it, it's less than 2% of the die area. No extra cost to the tape out. The logic is pretty sparse, so it just kind of compresses a little bit and it holds it in there. You could fit even more logic if you could find stuff to put in there, and there's no royalty to pay because it's open source. So basically, we can do it, and it's free. It's possible, and we can have the MMU now that we want to have that we couldn't have before. So okay, hitchhiking is theoretically possible, but who would give this guy a ride? And well, the good news is, luckily, there was a company called Crossbar that was already heading towards open source land, and they stopped and saw me on the side of the road and asked me for directions. And I said, hey, instead of giving you directions, how about I hitch a ride with you, right? And so these guys, I started a small company called Baochip, that's me, to hitchhike on top of the tape out. And the result is a chip called the Baochip-1x. It's a partially open RTL SoC for high assurance applications. And I've hitchhiked 5 open source CPUs onto this chip. There's a Vexris CPU core. Thank you. Which has an MMU in it, running at 350 megahertz and 4 pico-RV cores on it. It's got 4 megabytes of on-chip ROM, so it's RAM actually, and 2 megabytes of on-chip SRAM. So it's a fairly capable chip. Cryptography accelerators, true random number generator, USB high-speed cameras, I2C SPI, all these sorts of stuff, right? So what parts are open, what parts are closed? What parts are open is everything that computes, right? So the stuff that I contribute, the Baochip stuff is, of course, open, so the RISC-V cores and the I/O accelerator. And then Crossbar also committed to making a bunch of code open, particularly their cryptographic accelerators, most I/O interfaces, and the glue code between things. And all the firmware, the bootloader, everything is all open on this chip. The things that are not open are the things that don't or can't compute. So there is a Cortex M7 on the chip, but it's fused off in the Baochip version. It's incapable of running code. The details of the memory models, like how the testing is done and that sort of thing, is not available. The bus frameworks, AXI, HB, APB, so they're just passing data around. They shouldn't be changing data. Those things are not open. And the analog blocks, USB, and the PDK, of course, are not open in that case. But basically, everything that should be changing your data, you can inspect and see what's going on. And a bunch of stuff in between still has some progress to go before it's fully open. So it's not perfectly open, but it's perfect for keeping Xous on RISC-V, right? And so now that we have the RTL, what sorts of things can you do with it? Well, one of the cool things you do is you can do God mode time travel debugging with Verilator. If you've never seen what it looks like to debug with hardware, you can start a simulator, you can simulate your code, and you actually see the entire CPU state, including all the intermediate values in the registers, what the CPU is doing, the branch predictor state, all this sort of stuff. Everything is now just available to you forward and backwards in time. I extended a tool called GTK Wave, so you can hover over the program counter trace, and it can line up with the particular line of assembly code you're running at the time, so you can actually use this for debugging code, finding problems. You can prove that your constant code time. Oh, thank you. You can prove that your constant code time is constant time, right? So this is a routine that's involved in some cryptography stuff, and I was able to say that these 2 branch paths actually lined up perfectly. So instead of running benchmarks and guessing and seeing what things are, I actually say these are fully cycle accurate constant time parts. As a side quest, I want to also keep I/O open. You may have heard of the Raspberry Pi PIO block. It's a very cool thing. The problem is it's patented. So you can write all that sort of open source PIO code, but no one can build a PIO. Raspberry Pi has a monopoly on PIOs, right? And so I can't put one on my chip. So I came up with this thing I call the Bao protocol emulator. It can emulate any protocol with kind of a less than 25 megahertz toggle rate, cans, LED strips, the weird IR air conditioner protocol. It's open source and patent free. And basically, it's 4 pico-RV cores. Each of them has a 4 kilobyte local RAM that can run out of. And they talk to each other through a series of FIFOs. And they can also talk directly to the hardware. So very quickly, the 4 pico-RV cores are running RV3 to EMC. So it's compatible with existing tools. You actually can program it for directly using inline assembly in Rust. And with the E-E instruction set, only the bottom 16 registers are existing. The bottom to top 16 are like not mapped. And what I do is I take the top 16 registers and I map them to things like GPIOs and FIFOs at the end of the day. And so if you want to go ahead and toggle a GPIO, what you do is you would just move X1 to X21, which is a GPIO register, and the GPIO pins will change. You say, oh, but you can just do that with a load and store. Isn't it the same thing? The semantics of load and store, you can actually be blocked if the AXI bus is busy. So your GPIO will have a little bit of jitter in terms of time. Because this is actually moving between 2 registers, there's a defined amount of time this has to happen. So you get very cycle accurate access to the GPIO by having it directly inside the register set bank. If the cores, you have the 4 cores, they can talk to each other. You talk to them using the FIFOs. So if I want to send a message to another core, I just move a thing into the top of one of the FIFOs. And when the FIFO fills up, the core stops executing, and it blocks until the FIFO empties. If I want to receive a message, I read from a FIFO. So now if I have 3 cores, and I want to have those 3 cores sort of be in lockstep with the 4th core, I can have those 3 cores read from an empty FIFO, the block. The 4th core drops a message into the top of the FIFO, and now all of a sudden all 4 cores are running simultaneously in lockstep. And you can basically use that mechanism to synchronize to events, sort of external clock edges, clock dividers, that sort of stuff. So you don't have to cycle count all of your code in order to run at these slower clock rates. You just basically snap to a quantum. So BIO, software-defined I/O, it's 4 pico-RV cores, 4 kilobytes of code and private data RAM. Never have to say you're sorry. Future-proof, bug fixes and error checking and hardening can happen in hardware, and it's fully open source. There's a URL for it down there. You can build it yourself, put in your FPGAs, have fun with it. Please enjoy that, the BIO. Thank you. So putting it all together, this is a partially open RTL SoC. It's built for inspection, so that's the chip over there. It's mounted onto a board, and this is what it looks like when you go ahead and put it under Iris to have an inspection of it. It's built for running Xous on RISC-V, and it's built to break that power cycle of not being able to have security on these low embedded devices. So we now have an affordable SoC with an MMU. We have a small OS, Xous, that requires an MMU, but this is where we need your help. We need to basically show that the market actually wants, people actually want security in those low-end devices. So we're hoping that we can get people here to help us break the cycle together. So we have some free dev boards. These guys over here, they're available at the failover full assembly while supplies last. The full production will be in spring 2026. If you scan the QR code here, they'll take you to our Discord if you want to ask questions for us. I know that we're very short on time. If we have questions, we'll take them. But you can find us at the failover flow assembly or contact us on the socials for more information. And thanks very much for your attention.
Thank you very much. Bonnie and Zobs. So we're lucky you have you here. You said already you're in the failover flow area. Sorry, assembly. Yep. So the people here can ask their questions.
We have one question from the internet.
Yes, considering that logging is something you do often, it sounds very expensive to change ownership of pages for every message, because that means you need to invalidate the TLB. Also, the receiving server needs to unmap the pages quickly. How does your hardware design deal with that performance cost?
It's actually not too bad. I mean, our SRAM's directly on chip. It's just a few cycles to fill the TLB, walk the page table. There's a whole bunch of other stuff that actually is more expensive in terms of the overhead. So overall, benchmarking-wise, it's been acceptable, I would say, overall.
Yeah, there's also a TLB cache that's on the chip that makes it less expensive than it otherwise normally would be.
Yeah. So.
Thank you. You said you're still here for additional questions. Do you have an additional question from the internet?
Yes, there would be the question, what do you think about the RISC-V Cherry for hardware-enforced memory safety?
Yeah, I mean, I think I'm personally a big fan of capabilities and tag pointers. I love that sort of stuff. It was a big part of my doctoral thesis, actually. I think it just needs to mature and become a thing that's tape-out ready before we can start using it and see all the tools and everything come around it. Part of the idea is we want to have a chip that we could get out there and people start using now versus like waiting for ecosystems of tooling to come around. So there's a lot of emphasis in this project about making very standard, standard library, stable Rust, making things relatively simple so that people can just sort of absorb and start using it. And so yes, they're cool, fancy stuff. I think they're great. But we're just trying to do something relatively straightforward, I guess, inaccessible.
Also, one of the fun things about having a standard library that we're maintaining is that a lot of the things like pointer provenance are part of Rust and are being integrated within the standard library. So seeing that requirement come and having to update a lot of our standard library implementation to support that was kind of like, it keeps us on the front, the moving front. So being able to support that in the future is kind of something we've been making sure that we will have going forward.
Yep.
Thank you very much. Unfortunately, we're out of time. Please give a warm applause. Bonnie and Zobs.